Okay, so today we will discuss the definite and indefinite integrals. We have already discussed the Riemann integral of a function f, and we have defined the Riemann integral of a bounded function f defined over the closed interval a b as the upper sum f dx, which is equal to the infimum of the upper sum with a partition p, and lower sum a bar b f dx dx or f dx, which is the equal to the supremum value of the lower sum of f over the partition p, and supremum and infimum is taken over all such partition p, and whenever these two values coincide, then it is represented by a to b f dx, and we say it is a Riemann integral of a function f over the interval a b, and the class R is the set of all functions which are Riemann integrable, functions f which are Riemann integrable over the interval a b. We denote by this. So, f will be an element of this class. So, this is the way we have introduced the concept of the Riemann integral. Then an equivalent way of introducing the concept of Riemann integral is as follows. In a similar way, what we do is, let us suppose a function, let a function f x be defined, be bounded and defined on the interval a less than x less than b. Okay. Then partition this interval a b into sub interval by introducing the point x 1, x 2 and x n is b. So, partitioning these interval into sub interval. So, partition this interval a b into sub intervals by means of the points x naught, x 1, x 2, x n, where a is x naught less than x 1, less than x 2 and less than x n is say b. Okay. So, we are getting this part. Let us suppose, let delta x I is x I minus x I minus 1 be the length of the interval of the sub interval x I minus 1 to x I. Let us suppose this. Okay. So, let us again take this one a to b, a is x naught, here is x 1, say x 2, suppose this is x I minus 1, here is say x I, and then like this, and this will be x I. Now, what we do is we pick up the point, or choose the points instead of the or choose the points, choose the point instead of pick up, choose the points, take x I 1, x I 2, x I say n in the intervals in the intervals say x I minus 1 less than x I and less than or equal to x I, where I is 1 to up to n. So, in this we are choosing the point x I 1 here, say here x I 1, here x I 2, this is say x I and like continue this. Now, at this point find the functional value. Okay. So, now consider this sum sigma f of x I multiplied by the length of the interval in which this point x I lies, and I is 1 to n. This thing, take the limit of this sum when maximum of the length delta x I goes to 0, or this is equivalent to the same as limit as n tends to infinity, I is 1 to n f of x I delta x I. If this limit exists, if it exists, then denote this limit as a to b f x dx and is called, and then we say if this limit exists, if the limit 1, let it be 1, exists and independent of the partition P as well as independent of the choice of the points x I in the interval x I minus 1 to x I, then the value of the limit is denoted by integral a to b f x dx and is known as that the function f is Riemann integrable function. Integrable functions, okay, and the over the interval a b, okay. So, this is equivalent way that the previous one. What we simply here we are assuming the function is bounded function. So, f of x I cannot go to infinity, it will be remains less than bounded. So, whenever you choose the point x I 1, x I 2, x I any arbitrary point. So, basically the value of this, maximum value of this will be taken as this, is it not? So, it will, when the limit exists, means when this maximum delta x I goes, so the points are so close to each other that almost this entire line is covered and the curve will be something like. Now, in case if the function is continuous function, then this is we call it as a definite integral and it represents the area bounded by this. So, if the function f x is continuous over the interval a b, then integral a to b f x dx represents the area bounded above by the curve y is equal to f x, below y x axis and two ordinates x equal to a and x equal to b, and we call it this as a definite integral. We call it is a definite, but in general when f is a bounded function defined over the closed interval a b and it is Riemann integrable function, and it is Riemann integrable functions, then integral a to b f x dx, f x dx is known as f x dx, integral Riemann integral in the interval is called the definite integral of the function f x over this. So, this is basically it. When it is continuous, this represent the area, but if it is bounded, then also it will give some value, finite value. Okay. And we call it as a definite integral, because it cannot go beyond these two limits. F is called the integrand function. Here f is f x is the integrand, and a and b are lower and upper limits of integration. Limit of integration, and the interval a b is the range of integration. So, we have studied already in class 12th or etc., like integral a to b f x dx when f is continuous, and we call it term as a definite integral. So, here we are just extending the definition of definite integral for those functions which are Riemann integrable over the closed interval a b. So, this integral a to b f x dx, when f belongs to a Riemann integrable function, class of Riemann integrable function, will be termed as a definite integral. On the other hand, the function, the integral a to x f x dx or f t dt, so that this limit should not variable integration different, where f x is, or f t, you can say f t is integrable, is Riemann integrable, in the interval a x. In the interval a x is called the indefinite integral of f x, where the upper limit is a variable one. Here the upper limit is variable. Here upper limit is variable. That is why we call it indefinite here. This is also the indefinite integrals is also denoted as integral f x dx without limits, Okay. So, the only difference is when the integration is taken over some interval where the lower and the upper limits are fixed, then this integral, and f is a Riemann integrable function, then this is called a definite integral. When the upper limit is a variable one, then we call it as a indefinite integral. That is all. So, there are various properties of the definite and indefinite integrals. The property of definite integral is already we have discussed in a general way when we have discussed the properties of the Riemann stretch-range integral. So, when we take alpha x equal to x, it reduced to the Riemann integral, and a and b are fixed. So, it is a definite integral. So, the property which are already derived for this Riemann stretch-range integral will continue to hold good in case of the definite integral. Okay. So, we will just simply state those results without proof. So, properties of the definite integral. The first property is that we know if A is greater than B, then we say A to B f x dx. But if we reverse the order of this lower and upper limit, then we get this thing, and it follows from the definition that A to B f x dx is the same as minus times B to A f x dx. Second property says, if suppose the interval a b is given and there is a point C in between a b, then and f is Riemann integrable over the entire a b, then f is also Riemann integrable over this a c and c b, and integral a to b f x dx is the same as a to c f x dx plus c to b f x dx. And this also can be proved with the help of definition. What we do is we partition the interval a b in such a way, so that one of the partitioning point coincide with C, and then you apply the definition of the Riemann integral as a limit of the sum, you will automatically get these two things. So, nothing. And third condition is, if f x is integrable, over the interval a b, so is mod f x. That is, if f is Riemann integrable, mod of f is also Riemann integrable, and the integral and the modulus of integral f x dx a to b is less than equal to integral a to b mod f x dx. Again, this result follows from the definition, because when you start with the definition and take the limit of this sum, then limit is a continuous function, modulus is also a continuous function. So, you can take limit in modular inside the limit and then summation sign, you will get this result quickly. So, there is no much problem. However, here is a remark, the converse of this note, the converse of property 3 is not true in general. It means a function is such where the mod f may be Riemann integrable function, but f need not be a Riemann integrable function. For example, suppose if we look a function f x as 1 when x is rational, and minus 1 when x is irrational. Over the interval say 0 and 1, over this interval. Okay. So, over this interval we are choosing the function f, this is 0 1 interval. At the rational points, these are the rational points, they are very close to each other, the value of the function is 1, and for the irrational point the value of the function is minus 1, this minus 1. So, value of the function is minus 1, like this. So, continue this way. Okay. So, we get this function. Now, obviously, this function is not Riemann integrable function. Clearly, f does not belongs to Riemann integrable function over the interval a b. A b means 0 1 here, 0 1. Why? Because what is the upper sum of this? Because upper sum of this function f with respect to any partition p is nothing but what? Sigma, the value of meg mi into delta x I is 1 to n, is it not, upper sum, and this mi will be, when it is rational, it is 1. So, maximum value will always be 1. So, it is equivalent to sigma I is 1 to n delta x I, while the lower sum of this is nothing but what? 1 to infinity small mi delta xi, and that is equal to what? Mi is minus 1. So, it is sigma I equal to 1 to n delta xi. So, when you take the limit or take the infimum and supremum value of all such partition, then what we get? So, this implies that upper sum of f dx is 1, while the lower sum of this f dx is minus 1. So, they are not equal. Therefore, f cannot be a Riemann integral function over the interval 0 1. However, if we take mod of f, then mod of f means always 1 for all x belongs to the interval 0 1. Therefore, the Riemann integral a to b f dx, which is the limit of the f x and so on, limit of the sigma f of x I delta x I is 1 to n as n tends to infinity, is nothing but the b minus a, and here the b minus a will be equal to what? Is nothing but the 1. Okay. So, that is what. So, here this is 1, because a is 0, b is 1, and we get this. Okay. So, here a is 0, b is 1, b is 1. So, this is, so what he said, that mod f is Riemann integral function. Therefore, f mod of f belongs to R, but f is not in R. So, the converse is not true. Okay. Therefore, this. Now, fourth property is if f x is integrable, f x is integrable and non-negative in the interval a b, then the integral a to b f x dx is greater than or equal to 0. It also follows, because it is non-negative, so sum will be sigma limit of the sigma f x I, and sum f x I is positive, f of x I positive, delta x I is positive, sum will negate non-negative. So, limit will also be non-negative. So, there is nothing to prove it. Now, fifth property, if f 1 f 2 f n, if f I is x I is equal to say 1 2 and say n be integrable finite number of Riemann integrable functions over the interval a b, then and phi of f 1 f 2 f n, f 1 f 2 f n be a continuous function functions with regard to with respect to f 1 f 2 f n, with respect to these f 1 f 2 f n, then the function phi of x is integrable in the interval a b. That is, the meaning is if f I is continuous, f I is integrable function, f I is Riemann integrable function, and phi a t is continuous over the range of f I t, then the composite function phi of f t f I x is Riemann integrable. And this also we have proved in general for the Riemann stress integral. So, we know. Similarly, the sum of this is we can get it like this. Okay. Now, converse of this again sorry, as a remark note here, if suppose f is Riemann integrable, phi is also Riemann integrable, then there is no guarantee that phi of f will remain Riemann integrable. Okay. If f and phi, if f x and phi t are Riemann integrable functions, then phi of f x need not necessarily Riemann integrable. For example, let us take this problem. f x is, let f x is defined as 0 when x is irrational and is defined to be 1 by q when x is of the form p by q, p and q having no common factor. That is a rational number, and f x is comes out to be this, is a rational. So, clearly if you look clearly, function f is discontinuous at all irrational points, or sorry, all rational points, discontinuous at all rational points. Why? Because the reason is, suppose I take any rational point, suppose I take x equal to 1 by q, okay, then corresponding to for this there exists a sequence of irrational numbers, say t I, which goes to x, but what is the image of f t I? This f t I will always be 0. So, the limiting value will be 0, which is different from the f of x, because this is coming to be 1 by q, not 0. So, at every rational number is a point of discontinuity. Okay. But if we take the irrational number, okay, then if we take a rational number and take sequence of the rational, then q tends to infinity, it will go to 0. So, here you will get the continuity. So, this discontinuous functions are the points of rational points, and we know that set of rational numbers is countable and having measure 0. So, once it is countable and measure 0, so the function f is almost continuous function, almost everywhere continuous, because the point where it is discontinuous form a set of measure 0, and by definition result a function f is Riemann integrable if and only if it is almost everywhere continuous function. And so, by from the result that a function f belongs to Riemann integrable if and only if f is almost everywhere continuous. So, according to this we see, therefore, our f is belongs to the class R, is Riemann integrable function over the interval. Say I am choosing the interval any x is rational and say 0 1 I am taking, okay, no problem, 0 1. Okay. Now, let us take this over x belongs to here, which say x belongs to 0 1, clear, x belongs to 0 1 interval, p q no comment, q is not 0 of course, otherwise it will be problem. Now, if we look the function pi, let us consider the function phi, consider phi as the function where phi t is 1 when t is non-zero, n equal to 0 when t is 0, okay, over the same range of this same. So, obviously, phi has a point of discontinuity at t equal to 0, because limit point right and limit is 1, but the functional value is 0. So, it is a pointer which is again has a measure 0, which has measure 0, because singleton set has a measure 0. So, phi is integrable. So, f is Riemann integrable, phi is Riemann integrable. Okay. Therefore, what is the phi of f t? But phi of f x, if I take, then this value will be what? When x is rational, the value of f x is non-zero. So, according to this it will be the 1, and when x is irrational, the t is 0. So, value of the function is 0. So, it is 0. So, at the rational point it is rational number is not its value as 1 when x is n, 0 when it is irrational. So, this function phi f x is nowhere continuous. In fact, it is discontinuous function throughout this interval, because if you take rational number, again there is a sequence of irrational 0 0, which does not coincide with this. If you take a rational, sequence 1. So, it is throughout the interval it is discontinuous function. Therefore, a phi f x cannot be a Riemann integrable function, because the necessary and sufficient condition for a function to be Riemann integrable is it must be almost everywhere continuous function, but it is not almost everywhere, it is everywhere discontinuous. So, it is not. So, this shows that the continuity of the function phi is must. If one is f is Riemann integrable and phi is continuous, then the composite function will remain Riemann integrable. But if phi is also Riemann integrable, then you cannot say whether the phi of f x will be a Riemann integrable function. That is, composition of the two Riemann integrable function need not be Riemann integrable function. That is what he showed. Now, another fifth property is, if a sequence of functions f n x which are all Riemann integrable function or integrable in the interval a b converges uniformly to the bounded function f x in the interval of bounded function in the interval say a b, then f x is integrable, that is Riemann integrable, okay, and the integral a to b f x dx is nothing but the limit as n tends to infinity integral a to b f n x dx. That is all. So, what it says is, if a sequence f n is given to be integrable functions or Riemann integrable function, and it converges uniformly to f. When we say f n converges uniformly to x over the interval, it means f n x minus f x is less than epsilon for all x. It is independent. The epsilon delta does not depend that x is in respect. So, converges uniformly all n is greater than n naught. Then converges uniformly to a function f x in the interval a b. So, in f x minus f n is less than f for n is greater than equal to m, then f x is integrable and the n limit is the of this is the integral of this. Okay. So, let us see the proof of this. So, now, since f n x, these are the element of the Riemann integral functions. So, by necessary and sufficient condition of the result of the theorem that f belongs to R if and only if it is almost everywhere implies that each f n x is almost everywhere continuous function, almost everywhere continuous, almost everywhere continuous over the interval a b. This by definition. Okay. So, it means x the point where it is discontinuous will form a set of measure 0. So, let us pick up the point, let A be a point at which all the functions f n x are continuous. Let us take let a point alpha, let a alpha be a, because we have already used alpha be a point in the interval at which all the functions are continuous, So, this is okay. So, this is the a b and here is alpha where all functions are continuous. So, we can find out a small neighborhood of alpha, say alpha minus h to alpha plus h, where the fluctuation of the functions, f n x will lie between epsilon and minus epsilon, that is f of alpha minus h epsilon, f of alpha plus h. Okay. Each one of so f n, the fluctuation of this f n x is less than epsilon, that is f n x minus alpha f n x alpha plus epsilon. So, there exists. So, in this small so in a small neighborhood, alpha minus h alpha plus h of alpha, the fluctuation of f n x is less than epsilon for all values of n. This fluctuation, suppose this epsilon by 2, the fluctuation will remain less than epsilon. Okay. So, this part fluctuation there, but f n but given sequence f n x each is convergent or converges uniformly to the function f x. So, by definition, so modulus of f x minus f n x, this will remain less than epsilon for all n greater than m, okay, converges to them, and of course, every x in this. Okay, say therefore, the fluctuation of f x, therefore, if we take this interval alpha minus h, alpha plus h, and here is alpha. So, suppose I take a point x and y, then what will be the mode of f x minus f y? This is x and y both belongs to the interval alpha minus h, alpha plus h. So, if we take this thing, it is less than equal to f x minus f n x plus f n x minus f m x plus f m x minus f y. Now, this is less than epsilon, this is less than, so total is less than 3 epsilon. So, fluctuation of the function f x in the neighborhood of this is less than 3 epsilon. Therefore, f x is continuous. So, alpha is a point of continuity. So, this shows that alpha is a point of continuity for the function f x, because the fluctuation is this, and this shows that f x is, it follows, but alpha is arbitrary, it follows, because we can pick up any point where all the functions are continuous. So, those continuity point, those point at which the f n's are continuous will also at this point the function f x remains continuous. So, it means the function f x is almost, if it follows that the function f x, which is the limiting function, is the function f x is almost everywhere continuous over the interval a b. Okay. Once it continues, then let us find this integral. Consider the integral a to b f x dx minus integral a to b f n x dx. Now, this will be less than equal to what? Epsilon, because you combined it f x minus f n. So, it is less than equal to integral a to b f x minus f n x dx less than equal to, but this is less than epsilon. So, it is less than epsilon into b minus a, and hence integral a to b f x dx is the limit of this as n tends to infinity, integral a to b f n x dx. So, this proves. So, the uniform convergence of the function, if f n converges uniformly to f x, then f x will also be Riemann integrable, provided all f n's are Riemann integrable functions. Okay, and this integral. So, this proves the result. Now, again here we put a remark that condition of uniform convergence is must. The condition, the uniform convergence, the condition of uniform convergence of the sequence f n x to f x cannot be dropped, is essential, to get the above result, because if we drop this condition, the above result may not hold good. For example, suppose I take the sequence f n x is defined as n when x is less than equal to 1 by n and equal to 0 when elsewhere, when x is greater than 1 by n, elsewhere it is 0 in the interval 0 1, x belongs to the interval 0 1, let it be okay, 0 1. So, what we see here is the function f 1, this is a interval 0 1, the f 1 x, f 1 is less than equal to 1, f 1 functions is less than 1 and so on. F 2 is, says, suppose n is this, 1 by n is this, 1 by n is this. So, what is this function is? The function f n is such, the all x when lying between 0 and 1, the value of the f n x is n, this is n, this is n. So, here it is f n x is n, and as soon as it crosses, it comes out to be here 0. So, f n x is defined like this. So, for each n, f n x has only one point of discontinuity. F n x has only for each n, f n x only one point of discontinuity that is at x equal to 1 by n in the interval 0 1. Because prior to this the value of the function is 1, after right hand value of the function limit value is 0. So, basically both are not coinciding. So, it is a pointer. So, each f n x is almost continuous, almost everywhere continuous functions, almost everywhere continuous. Therefore, f n x, each f n belongs to the Riemann integrable class of 0 1. So, integrable. So, it is integrable. So, each of f n is integrable function. So, in each f n is integrable, and the value of this integral 0 to 1 f n x dx, this is equal to 0 to 1 by n f n x dx, and f n x 1 by n is n. So, basically it is 1. Okay. But what is f x? F x is limit of this f x as n tends to infinity. Now, limit of this f n x, when n is sufficiently large, it means this point is coinciding almost 0. So, the limiting value will be 0, because after this the value will be 0. So, it is 0. So, limiting value of this is 0 for 0 less than x less than equal to 1, but which is different from this one 0 to 1, 0 to 1, 0 to 1. So, therefore, 0 to 1 f x dx is 0, which differs from the limiting value of 0 to 1 f n x dx. Clear? Because the limit of this is 1. So, limit of this 1 and here it is 0. So, we get contradiction, and this is because the sequence are not convergent uniformly to the function f, because when you take the f n x and f n minus f n, it is not less than f sin r. So, it depends on the points f sin r, therefore, it is coming. Okay. Now, we go for some properties of indefinite integrals also. So, let few properties of the indefinite integral. Okay. When f x is bounded, then this integral a to x f t dt, this integral let us denote by capital F x, because as x changes the value function f x changes. So, when let f x be a bounded function, let f x be a bounded function and integrable over the interval say a b. Okay. The indefinite integral f x, which is a to x, is obviously is a function of x, because it changes its values with respect to the upper limit. Okay. So, let us denote this value by f x. Okay. Now, we have one result. The first theorem says, if f x is this, let it be 1, the function f x which is defined as 1, defined by 1, okay, is a continuous function of x, in the closed interval a b, it is also absolutely continuous. It is also absolutely continuous function, continuous over the interval a b. Okay. So, how to prove it? Let us consider f of x plus h minus f of x minus f of x. So, this is equal to a to x plus h f x dx minus a to x f t dt, sorry, f t and f t dt, f t dt. Okay. So, this will be, this is x f t dt. Now, this will be equal to integral x to x plus h f t dt. Okay. Now, let f dash be the least upper bound for this. So, what we do is, so the modulus of this, so mod of f x plus h minus f x is less than equal to integral x to x plus h modulus of f t dt, which is less than equal to say m dash into h, where m dash is the maximum of the mod f t when t ranges from this interval, the maximum value of the function over the interval a b. Okay. Now, as h tends to 0, the right hand side goes to 0. So, the limit of this f x plus h as h tends to 0, this coincide with f x. Clear? Similarly, if we start with minus sign, we will get the minus sign here, we get the minus sign here, we get the minus sign here, we get the minus sign here, and rest. It means left hand right limit both coincide and coincide with f x, the value of the function. So, this implies the function f x is continuous, which we wanted to show in a closing, and x is a point, arbitrary point in this. So, it is continuous in this. Now, if I take the intervals, sufficiently small intervals a 1, b 1, etc., which suppose we take if a 1, b 1, a 2, b 2, and say a n, b n, and so on, be finite, all countable set of non overlapping intervals of total length, measure or length, total length, that is called the measure also, total length less than h, contained in the fundamental interval a b, contained in the fundamental interval a b, then we have sigma mod of f b r minus f of a r, mod of this is less than equal to m dash sigma b r minus a r over r, and this length is less than h, which is less than epsilon r when we choose h to be say epsilon by m dash. So, what we say here, that for a given epsilon greater than 0, we can find an h such that whenever the points are inside this sigma of b r a r, the sum of these finite or countable interval is length is less than h, then this entire sum is less than epsilon r. So, this shows that function f x, this is also a function f x is absolutely continuous function. absolutely continuous over the interval a b. Okay. So, this will be so this here we will stop it, and next time we will continue with the same. Thank you very much.